Take a moment and let yourself settle. You finally found a quiet place to rest. The lights fade. Your breathing softens. And for a moment, it feels as if everything, your body, your house, your world, has finally stopped. But it hasn't. In fact, you are traveling faster than anything you've experienced today. As you exhaled just now, you traveled farther than many people drive in an hour. In the last minute, you drifted across more distance than the width of the state you live in. And you did it all without taking a single step. Because beneath you, the Earth is spinning at nearly 1,600 kilometers per hour, pulling you eastward whether you notice it or not. At the same time, you and everyone you know are racing around the sun at 30 kilometers per second, a speed so fast that every 60 seconds you move farther than most countries are wide. The sun itself is not standing still either. It's towing the entire solar system around the center of the Milky Way at 220 kilometers per second, along a massive stellar highway tens of thousands of light years long. And the Milky Way? It's not drifting lazily in space. It's sliding toward Andromeda at 110 kilometers per second, the opening steps of a slow-motion collision already underway. Zoom out further. Our local group of galaxies is falling toward the Virgo cluster. Virgo is falling toward the Great Attractor. The Great Attractor toward the even larger Shapley concentration. And the entire supercluster we belong to, Laniākea, is drifting like a continent of galaxies through cosmic waters. And all of that is happening inside a universe whose very fabric is stretching, expanding, carrying everything farther from everything else. Your pillow, your room, your planet, your star, your galaxy, everything is in motion all at once. Which brings us to the question at the heart of tonight. If everything from your pillow to your planet to your galaxy is moving, where is everything actually going? Tonight, we'll follow that question as far as it can take us. We'll step into the minds of the ancient astronomers who once believed Earth was the center of everything. Although we can't know which path the universe will ultimately choose, we can explore the three cosmic endgames now on the table. The Big Rip, where acceleration becomes so extreme that galaxies, stars, planets, and even atoms are torn apart. The Big Crunch, where expansion reverses and everything collapses back into a single, searing point. The Big Freeze, the quiet fading of everything as starlight dims, matter decays, and the cosmos cools toward eternal darkness. These aren't just theories. They are possible futures written into the physics of motion itself. And now, to understand where everything is going, we first have to look back toward a time when we believed everything was going around us. For most of human history, the night sky looked perfectly still. Night after night, the same patterns returned. The constellations didn't drift. The stars didn't slide across the sky. Everything above us seemed fixed in place, calm, predictable, unchanging. From that view, one idea felt completely natural. We must be at the center. This belief appeared in ancient Greece, China, India, the Middle East, and the Americas. Different cultures, different tools, same conclusion. If the heavens don't move, then we must be the still point. That idea became formalized through the work of Ptolemy, a brilliant astronomer of the 2nd century. In Ptolemy's model, Earth, sat motionless at the center. The sun, moon, and planets moved around us. The stars were attached to a vast outer sphere, but there was a complication. Planets sometimes slowed down, stopped, and appeared to move backward in the sky, a behavior called retrograde motion. To account for it, Ptolemy added small circular paths called epicycles, placed on top of larger circular orbits. His system looked complex, but it worked surprisingly well. It predicted planetary positions with enough accuracy to last more than 1,000 years. For a long time, no one questioned it. And yet, behind all the clever geometry was a simple problem. We were asking the wrong question. Ancient astronomers assumed, why does everything move around us? That question itself was the mistake, because the Earth was never the thing being orbited. It was the thing doing the orbiting. The first major correction came from Nicholas Copernicus in the 1500s. He suggested something bold for his time. The sun, not the Earth, sits near the center of our planetary motions. In his model, the Earth spins on its axis, orbits the sun once every year, and tilts, giving us seasons. With that single shift, retrograde motion suddenly made sense without epicycles. Planets weren't looping backward. We were simply overtaking them as we moved along our own orbit. For the first time, the solar system became a simple, elegant structure. Not perfect. Copernicus still assumed the orbits were circles, but far closer to the truth than anything before it. And with that shift came a deeper realization. We were never the center. We were passengers in motion. This wasn't just a scientific adjustment. It was a change in perspective. Once Earth moved out of the center, the entire map of the universe changed with it. The question transformed from, why does everything orbit us, to where are we going? Because movement looks different depending on where you stand. If the observer is moving, then every other object appears to move in a way that can be misleading. Imagine sitting on a slowly turning carousel, watching the world slide around you. If you didn't know the platform was spinning, you'd think everything else was drifting in strange curves. That was humanity for 1,000 years. We saw motion in the sky, but misunderstood its direction because we assumed we were standing still. Carl Sagan put it simply, we are not at the center of anything. Once Copernicus shifted our point of view, the universe opened up. Planetary motion became clearer. Earth's role became clearer. And a path appeared, a path that eventually led us to discover the true structure of the Milky Way, the local group, and the motion of galaxies themselves. But that next step requires one more idea. Because if we're moving too, then the way we measure motion must be reconsidered. Everything depends on the vantage point, the frame of reference. Once we understood that Earth was in motion, the next step was learning how to see motion clearly and measure it with enough precision to know where anything was actually headed. That shift began with Galileo Galilei, a man who pointed a small telescope at the sky and found that the heavens weren't smooth or perfect at all. When he looked at the moon, he saw mountains, shadows, and deep craters, signs that the moon was made of real, solid rock, not some flawless celestial material. When he looked toward Jupiter, he found 4 small moons orbiting the giant planet. A simple observation, but powerful. If those moons were not circling Earth, then not everything in the universe revolved around us. and the phases of Venus told an even clearer story. They only made sense if Venus was orbiting the Sun, not Earth. For the first time, the sky wasn't mysterious. It was measurable. A place where careful observation could overturn ideas held for centuries. But seeing motion was only the beginning. We still needed to describe it, with rules, patterns, and mathematics. That's where Johannes Kepler stepped in. Studying Tycho Brahe's detailed observations, Kepler found the true patterns hidden inside planetary paths. He discovered 3 elegant laws. First, planets move in ellipses, not perfect circles. Second, they sweep out equal areas in equal times, meaning they speed up and slow down in a predictable rhythm. Third, a planet's orbital period is linked to the size of its orbit, a deep harmony that repeats throughout the solar system. Kepler didn't just fix the old model. He revealed the geometry of the solar system. For the first time, motion wasn't guesswork. It followed rules that could be written down and trusted. If you've ever watched a car speed up as it exits a curve, you've seen a simple version of Kepler's second law. Even something familiar on Earth connects to the movement of worlds. But one question remained. Why did the planets move this way? In the late 1600s, Isaac Newton gave the answer. An answer that unified the sky and the Earth under the same idea: gravity. Newton showed that the same invisible force that pulls an apple downward is the same force that holds the moon in its orbit, and the same force that keeps Earth circling the sun. One law rules the falling apple and the orbiting planets. Gravity wasn't mystical. It wasn't tied to perfect shapes. It was universal, predictable, and mathematical. A single framework explaining motion from stones tossed by hand to planets moving through space. And with Galileo, Kepler, and Newton together, the full picture finally emerged. Galileo showed what was moving. Kepler revealed how it moved. Newton explained why. For the first time in human history, motion itself could be described with equations, simple, clear equations that worked on Earth and in the sky. Newton later wrote, "If I have seen further, it is by standing on the shoulders of giants." And thanks to those giants, we now had the tools needed to measure movement on every scale. From planets to stars to galaxies. The universe was no longer a mystery of circles and guesses. It was a place ruled by laws we could understand. By the time Galileo, Kepler, and Newton revealed how motion worked, a new question naturally appeared. Now that we understood the rules, where exactly were we inside the universe? For centuries, the night sky had looked like a single, endless sheet of stars. No depth, no structure, just a bright band across the darkness. But in the late 1700s, a musician turned astronomer named William Herschel, working side by side with his sister Caroline, decided to do something no one had ever done before: count the stars, all of them, region by region. Night after night, they surveyed the sky through their telescopes. They pointed at one small patch, counted every star they could see, then moved to the next. Slowly, patiently, they built a map, not of the Earth, but of the structure of the heavens. And what Herschel found was stunning. When he plotted the number of stars in different directions, something emerged. A shape. Long, wide, and thin. Not a sphere, not a dome. A disk. A great flattened system of stars. Brightest and most crowded toward the middle. Thinner and more diffuse toward the edges. The first rough portrait of our home in the universe. Today, we call it the Milky Way galaxy, a vast island of hundreds of billions of stars. But one detail stood out immediately in Herschel's early map. The sun wasn't at the center. It was off to the side, tucked in a modest neighborhood, far from the dense galactic core. It was a quiet, humbling realization. Our star is ordinary. Our location is ordinary. Even our place within our own galaxy is not central or special. And with that realization came a deeper shift in perspective. The Milky Way wasn't the universe. It was just one island among many, floating in a much larger cosmic sea. Herschel's map wasn't perfect. He didn't yet know about the clouds of interstellar dust that blocked much of the starlight, making the galaxy appear smaller and more uniform than it truly is. He didn't see the spiral arms, or the bar-shaped core, or the halo of dark matter that surrounds it. But even with those limitations, he grasped something essential, something no one before him had. We live inside a structure, a system, a galaxy with shape, boundaries, and motion. We inhabit the luminous part of a vast system, Herschel wrote. A simple sentence, but a giant leap in understanding. Because once you accept that the sun is just one star among hundreds of billions, another realization follows naturally. Everything the sun does, every orbit, every path, every direction, is only a tiny part of the motion of the entire Milky Way. If our solar system is a small boat, then the galaxy is the ocean it sails on. And if we want to understand where the sun is going, we can't just look at its own orbit. We have to understand the motion of the entire island it belongs to. The question had turned into a bigger one. What is our galaxy doing? Because if the sun is inside a massive spinning disk of stars, then the real question is, where is the galaxy itself going? Imagine you're sitting on a train. The cabin is quiet. You're relaxed, looking out the window, waiting for the ride to begin. Then, suddenly, the train next to you starts to move. And for a split second, you feel something strange. Am I moving? Or is it the other train? Your body hasn't shifted. Your seat hasn't shaken. But the world outside your window slides sideways, and your brain tries to decide which story to believe. That tiny moment of confusion is the perfect doorway into one of the most important ideas in physics, a frame of reference. A frame is simply the place you choose to stand while judging motion. If you choose the frame of the train you're sitting in, then you feel still and the world moves. If you choose the frame of the ground, then the train is the thing in motion and the platform stays still. Nothing magical is happening. Just two different perspectives describing the same event, both correct within their chosen frames. And this leads to a quiet but powerful truth. There is no such thing as absolute rest, only rest relative to something else. This idea becomes essential the moment we look up at the sky. From the frame of the Earth, the sun rises and sets. It arcs overhead. It seems to circle around us. But shift your frame to the sun, and the entire picture flips. The Earth rotates on its axis and orbits the sun, not the other way around. Shift again to the frame of the Milky Way, and now you see the sun, along with Earth and every planet, moving around the center of a spiral galaxy. Same motions, different frames, different descriptions, and all of them true in context. This is why ancient astronomers weren't foolish when they thought the sun moved around the Earth. from their frame, the ground beneath their feet. That's exactly what it looked like. Motion always depends on where you choose to stand. The same rule applies on the scale of galaxies. If you choose the frame of the local group, you'll see that the Milky Way and Andromeda are slowly drifting toward each other, drawn by gravity. But if you choose the frame of expanding space, the story changes. The fabric of the universe is stretching, and both galaxies are being carried away from more distant galaxies. Two different perspectives, two different descriptions, but both mathematically valid. This is the key to our bigger question tonight. Where is everything going? There is no single answer, no single direction, no single universal map. Every scale, Earth, solar system, galaxy, supercluster, has its own motion, and that motion looks different depending on the frame you choose. Right now, as you lie in your room listening to this, you can choose any frame you want. From the frame of your bed, you're still, perfectly still. But from the frame of the Milky Way, you are racing around the galaxy at hundreds of kilometers per second. From the frame of Laniākea, your entire galaxy is drifting along a river of thousands of galaxies. And from the frame of the expanding universe, you are being carried outward on a tide of space itself. None of these perspectives cancels the others. All of them describe a different piece of the same reality. As Einstein famously pointed out, there is no preferred frame of reference in the universe. Motion is not about truth. It's about perspective. And once you understand that perspective shapes every answer, the next step becomes much clearer. If the sun sits inside a vast galaxy, and if motion depends on where we choose to stand, then what happens when we zoom out one more level? Now that we understand motion, from falling apples to orbiting planets, it's time to zoom out again. Because the sun, the warm, familiar star that anchors our days, is not sitting still in space. It has an address, a speed, a path, a role inside something much larger. To see that bigger picture, we start with the shape of the galaxy we live in. The Milky Way is not a cloud of random stars. It's a vast spiral galaxy, a rotating disk tens of thousands of light years across, with sweeping arms made of gas, dust, and hundreds of billions of stars. Our sun is not on one of the grand, bright spiral arms. Instead, it sits inside a smaller, quieter branch called the Orion Arm, sometimes called the Orion Spur, a kind of side street in the galactic city. And the first people to map this city were an unlikely pair. William Herschel and his sister Caroline, counting stars and sketching the rough layout of the galaxy long before photography, radio telescopes, or space observatories existed. But the next great leap, the one that told us how the sun moves inside this system, came from a Dutch astronomer named Jacobus Kapteyn. Kapteyn studied the motions of thousands of stars. He measured tiny shifts in their positions, their proper motions, and noticed something surprising. Stars weren't drifting randomly. They moved in patterns, streams, with two preferred directions across the sky. After recalculating those motions in a galactic frame of reference, Kapteyn realized something remarkable. The sun itself is moving through the local stars. It isn't sitting in place inside the Orion Arm. It's swimming through it, and it's moving toward a specific point in the sky, a direction astronomers later called the solar apex, located in the constellation Hercules. The speed? About 20 kilometers per second. Nothing flashy, not loud, not dramatic, but steady, adrift through our local neighborhood of stars. Then came Jan Oort, who refined this picture even further. Oort analyzed the motions of stars across many directions and discovered something crucial. The Milky Way rotates, and it rotates in a way called differential rotation. Stars closer to the galactic center move faster. Stars farther out move slower. It isn't a rigid wheel. It's a flexible disk of orbits, each with its own speed. And with Oort's analysis, the Sun's full address became clear. It sits roughly 8 kiloparsecs, about 26,000 to 27,000 light years, from the center. It orbits the galaxy at around 220 kilometers per second. One full lap around the Milky Way takes about 225 million years, a galactic year. To put that in perspective, the last time the Sun completed a full orbit, dinosaurs were just beginning to appear on Earth. But what exactly are we orbiting? At the very center of the Milky Way lies something we cannot see with our eyes. Sagittarius A, a supermassive black hole weighing a few million times the mass of the Sun. We know it's there because stars near the center move in tight, fast loops, as if whipped around by an immense gravitational anchor. Andrea Ghez, one of the astronomers who studied these stars, said it simply: at the heart of our galaxy lies a supermassive black hole that keeps everything in orbit. And you, right now, lying on your bed, breathing quietly, are moving around that black hole, not falling into it, not spiraling downward, but riding a stable orbit along with billions of other stars. You are orbiting something you will never see, something completely silent, something unimaginably massive. It's one of those truths that makes you stop for a moment. Your cosmic address is not just Earth. It's Earth, orbiting the Sun, on a small arm of a spiral galaxy, circling a supermassive black hole. Every second you lie here, you move thousands of kilometers along that galactic path without ever feeling a thing. And so, in the frame of the Milky Way, the answer to where is everything going becomes simple. Everything in our local neighborhood is going around the dark heart of our galaxy. But that's only true in this frame, the galactic frame, because the Milky Way itself is not drifting quietly in place. It too has a destination, a direction, a journey of its own. The Milky Way feels enormous when we think about our place inside it. A vast spiral of stars, dust, and gas turning slowly around a supermassive black hole. But even a giant can have neighbors, and ours is a particularly impressive one. Across the darkness, about 2.5 million light years away, lies Andromeda, the closest large spiral galaxy to our own. It's broad, bright, and structured much like the Milky Way, possibly even a bit larger. If the Milky Way is a grand island of stars, Andromeda is the next great continent across the cosmic ocean. For centuries, astronomers wondered, is Andromeda drifting away or drifting toward us? The answer came from light itself. When we look at distant galaxies, we can measure how their wavelengths shift. If the light stretches toward red, the galaxy is moving away. If it shifts toward blue, it's coming closer. Andromeda shows a spectacular blue shift. It isn't being carried away by the expansion of space the way most galaxies are. It's moving toward us, fast, hundreds of kilometers per second. But motion toward us only tells part of the story. Astronomers also needed to know how Andromeda moves sideways, its proper motion. Measuring this tiny angle took decades, but once it was solved, the picture became clear. The Milky Way and Andromeda are on a slow, inevitable collision course. Not tomorrow, not next century, but in roughly 4 to 5 billion years, the two dominant galaxies of the local group will begin to merge. It won't look anything like the fiery impacts we imagine from movies. In fact, because galaxies are mostly empty space, the experience is more like watching two fog banks drift into each other, slowly, silently, beautifully. If someone sped up time millions-fold, this is what they'd see. Phase 1. The first approach. As Andromeda grows larger in the night sky over hundreds of millions of years, the outer halos of both galaxies begin to touch. Stars in the outskirts stretch into long arcs, tidal tails, drawn out by gravity's pull. Phase 2. The first passage. The two galactic disks pass through one another. Their cores swing by, creating a moment of intense gravitational distortion. Stars don't crash into each other, but their orbits shift, forming bridges of starlight connecting the galaxies. Phase 3. The long dance. After passing once, the galaxies loop back, drawn together again. They pass through each other a second time, then a third. Each encounter mixes their stars more thoroughly. Phase 4. The merger. Eventually, after billions of years of this slow-motion choreography, friction within the dark matter halos drains energy from the system. The Milky Way and Andromeda settle into a single, larger galaxy, likely an enormous elliptical system that astronomers already have a name for, Milkymeda. And where will the Sun be? Probably on a different orbit, maybe thrown farther out, maybe drifting into a new stream of stars, but almost certainly still intact. The chance of our Sun hitting another star is incredibly small. Even inside a galactic collision, the distances between stars are huge. Far more empty space than solid matter. So what does all this mean for our big question? On the scale of the local group, the answer to where is everything going has a clear, definite component. The Milky Way is moving toward a merger with Andromeda. Every moment you lie here listening, the distance between the two galaxies shortens by a tiny amount. Not enough to notice, not enough to feel. Just enough that, over long cosmic timescales, the future is already written. If you closed your eyes for 1 billion years and opened them again, the sky would be unrecognizable. A sprawling, distorted ballet of two massive spirals blending into one. But for tonight, the collision is only a quiet fact, a distant destiny, something your galaxy is gently moving toward, one heartbeat of the universe at a time. Avi Loeb once said, "The future night sky will be dominated by the glow of a merged Milky Way and Andromeda. A new home, a new galaxy, a new shape for everything we know." If watching two galaxies drift toward a merger feels grand, it's only because we haven't yet looked beyond them. The Milky Way and Andromeda might seem enormous, but together they form only a tiny neighborhood in a much larger landscape. A landscape filled with hundreds, thousands, even hundreds of thousands of galaxies. The first step outside our galactic boundary is the local group. It contains the Milky Way, Andromeda, the smaller Triangulum galaxy, and roughly 80 dwarf galaxies scattered around them. It stretches about 10 million light-years across, a loose collection of islands bound together by gravity. Within this group, galaxies move, drift, and orbit in long, slow arcs. Nothing chaotic, nothing rushed, just the gentle gravitational pull between neighbors who share the same cosmic address. But even the local group is small. Zoom out, and you enter a region once called the Virgo supercluster, an area containing thousands of galaxies, all influenced by the central Virgo cluster, a massive knot of galaxies sitting tens of millions of light-years away. The Milky Way and Andromeda are not falling into it quickly, but they are drifting in its direction, slowly, steadily, as if pulled by a distant valley in the landscape of gravity. For a long time, astronomers thought the Virgo supercluster was the true continent of our part of the universe. But the real breakthrough came only recently, when researchers combined maps of galaxies with maps of their velocities, the directions they were actually flowing. A team led by R. Brent Tully realized that galaxies weren't just sitting in clusters like marbles in a bowl. They were moving along paths, following the gravitational terrain. Those paths, those flows, revealed the true shape of the region, and that region was far larger than anyone expected. They named it Laniākea, Hawaiian for immeasurable heaven, a structure 500 million light-years wide, containing around 100,000 galaxies. It is not defined by where galaxies are. It is defined by where they are going. And that's where the idea of rivers of galaxies comes in. Imagine standing on a mountain, looking down at a landscape. You can see valleys and ridges. You can see how water will naturally flow downhill, following the contours of the land. Now, replace water with galaxies. Replace hills with overdensities of dark matter. Replace valleys with gravitational basins. In Laniākea, galaxies flow the way rivers do, sliding along invisible gradients, drifting toward regions where mass is concentrated. Some flows stretch hundreds of millions of light-years. Some converge, some branch apart. But they form a pattern so elegant that when you see the full map, it's impossible not to feel awe. Galaxies are not wandering randomly. They are streaming, like leaves on the surface of a vast, slow-moving cosmic river. And the Milky Way? It's inside one of these rivers. Our local group sits along a gravitational pathway that leads toward a dense region known as the Great Attractor, a basin of mass deep enough to tug thousands of galaxies in its direction. That doesn't mean everything is falling into a single spot. Space is expanding, clusters are moving, and dark energy is pushing outward. But within the gravitational landscape of Laniākea, the direction of motion is clear. Everything here, every galaxy, every cluster, every group, is flowing along gravitational rivers toward the deepest valleys of the supercluster. This brings us back to our guiding question: where is everything going? On the scale of Laniākea, the answer is this: everything is sliding along the cosmic terrain, drifting toward the largest concentrations of mass in the region. Not because of momentum alone, but because gravity shapes the very flow of space. And as you lie still tonight, you are part of that flow. Not just your planet, or your star, or your galaxy, but your entire supercluster is gliding across a gravitational map that stretches 500 million light-years wide. A reminder that you don't just live in the Milky Way, you live inside a river of galaxies. Brent Tully summarized it beautifully. Laniākea is defined not just by where galaxies are, but by where they are going. And to understand where everything in Laniākea is going, we have to confront the two forces shaping that flow: a massive pull and a mysterious push. Until now, our cosmic map has grown in smooth, predictable steps, from planets to a galaxy to a group of galaxies to entire rivers flowing across Laniākea. But the moment we ask why these rivers flow the way they do, the tone of the universe changes, because the answer is hidden behind a curtain, a literal one, the zone of avoidance. A blind spot in our sky. The Milky Way is beautiful when seen from Earth, a silver band of starlight stretching across the night. But that beauty comes with a cost. Our galaxy contains enormous clouds of dust, thick enough to block a significant portion of the sky. This region is known as the zone of avoidance. For decades, it was a missing piece of the puzzle, a blank spot on our maps, a direction in space where we simply could not see what was there. And yet, the motions of galaxies around us hinted that something massive was hiding behind that dust. Something we couldn't see, but something strong enough to pull entire clusters of galaxies in its direction. X-ray, infrared, and radio. Tools that open the curtain. Eventually, new eyes pierced the darkness. X-ray telescopes revealed high-energy sources hidden behind the dust. Infrared observatories saw through the obscuring lanes and detected galaxies we never knew were there. Radio astronomy traced clouds of hydrogen and pinpointed masers, cosmic beacons whose motion we could measure precisely. Together, these tools began to sketch what lay inside the zone of avoidance. And what they found changed everything. See Norma Cluster and the Shapley supercluster. One of the first clues was the Norma Cluster, a massive, dense cluster of galaxies sitting right behind the dusty disk of the Milky Way. But the real revelation was farther out. The Shapley supercluster, one of the largest and densest structures in the nearby universe. Shapley contains thousands of galaxies, bound together in a gravitational basin so deep that its presence shifts the motion of galaxies tens of millions of light years away. It was like discovering a mountain range in a landscape you thought was flat. And suddenly, the motions of galaxies around us made more sense. The Great Attractor, a hidden gravitational valley. When astronomers measured the velocities of nearby galaxies through surveys like cosmic flows, they noticed something striking. Galaxies were drifting toward the same region of space, not chaotically, not randomly, but in a shared direction, straight into the zone of avoidance. They named this unseen pull the Great Attractor. It's not a single object, not a black hole, not a star cluster. It's a region of space filled with an enormous concentration of mass, including clusters like Norma and the greater Shapley concentration behind it. In essence, the Great Attractor is a gravitational valley, and Laniākea is sliding downhill. Every galaxy in our home supercluster, the Milky Way included, is drifting into that valley, pulled by the mass hidden behind the dust of our own galaxy. The dipole repeller. The push. That isn't a push, but gravity alone is not the complete story. On the opposite side of Laniākea lies a vast region that is nearly empty, a cosmic void containing very little matter. Astronomers call it the dipole repeller. Despite the name, it isn't pushing anything. Voids do not repel. They simply lack the gravitational pull that dense regions have. A useful way to picture it: you don't fall because the ground pulls you downward. You fall because nothing is holding you up. Likewise, galaxies are not accelerated because the repeller pushes. They accelerate because nothing there is pulling them back. The combination of pull from the Great Attractor and lack of pull from the dipole repeller creates the full motion of Laniākea, a cosmic push and pull without the push. F. The flow of Laniākea. Put together, the picture becomes clear. Galaxies flow downhill toward dense regions like the Great Attractor and Shapley. They drift away from the repeller because it cannot hold them. The entire supercluster, hundreds of thousands of galaxies, shares this movement. It's a river, shaped not by water, but by gravity and emptiness. A river with a direction. A river we are inside right now. G. Bringing it back to you. As you lie still tonight, you are moving along that flow. Earth drifts through space. The sun swims through the Orion Arm. The Milky Way glides within the local group. Laniākea slides toward the hidden gravitational valley of the Great Attractor. You cannot see it. You cannot feel it. But your entire cosmic home, everything you've ever known, is on that journey. H. A temporary answer to the title. On the scale of the supercluster, the answer to "Where is everything going?" is simple. Everything in Laniākea is flowing toward the Great Attractor and drifting away from the dipole repeller. As Brent Tully put it, we live in a region of space where thousands of galaxies share a common destiny. And yet, this still isn't the end of the journey. There is a force larger than gravity shaping the ultimate fate of the universe. For everything we've talked about, planets orbiting stars, stars orbiting a black hole, galaxies drifting through Laniākea, there is a deeper layer of motion running underneath it all. A motion so large, so steady, and so quiet that for most of human history, we had no idea it existed. That changed in the 1920s, thanks to a simple but revolutionary observation by Edwin Hubble. A. Hubble's discovery. Galaxies, our redshifted astronomers, had begun measuring the light from distant galaxies, and something curious kept appearing in the data. Almost every distant galaxy showed a redshift. Its light stretched toward longer wavelengths. At first, it seemed like each galaxy was simply moving away from us. But then the pattern sharpened. The farther away a galaxy was, the faster it seemed to be receding. This relationship became known as Hubble's law. Edwin Hubble described it simply. The farther away a galaxy is, the faster it appears to be receding. This wasn't random motion. This was structure. This was a signal. And the signal said, the universe is expanding. But the real shock was yet to come. B. The universe isn't objects moving. It's space stretching. When people first hear about galaxies moving apart, they imagine galaxies flying through space like shrapnel from an explosion. But that's not what's happening. It isn't galaxies rushing through space. It is space itself that is stretching. To picture it, imagine a loaf of bread rising in the oven. As the dough expands, The raisins inside move farther apart, not because the raisins are moving, but because the dough between them is stretching. Or think of points drawn on the surface of a balloon. As you blow air into it, every point moves away from every other point, even though none of the points are crawling across the surface. That's what the universe is doing. It's a balloon with no center, no special starting point, no privileged location. To every observer, no matter where they stand, the universe appears to expand outward from them, not because they are the center, but because there is no center. That's the twist. Space doesn't expand from somewhere. It expands everywhere. See what it really means for motion. The expansion of the universe isn't a force. It doesn't push. It doesn't shove galaxies apart. It is simply a property of space-time, a background flow, a quiet, steady stretching that underlies everything. This stretching creates a baseline motion that galaxies drift along, whether they want to or not. Even as galaxies fall toward the Great Attractor, even as clusters pull on each other, the fabric beneath them is expanding. D. Local motion versus cosmic expansion. The tug of war between gravity and expansion shapes the entire universe. Within the local group, gravity wins. The Milky Way, Andromeda, and the dwarfs between them remain bound together. Expansion doesn't pull them apart. Outside that small region, expansion gradually takes over. The farther two galaxies are separated, the stronger expansion becomes. It's like standing in a river. The flow is gentle near the banks, but in the middle, the water moves faster. At enormous distances, hundreds of millions of light years, expansion dominates all other motions, which means galaxies aren't just going somewhere. They are being carried somewhere by the expansion of space. E. How this changes our big question. So when we ask, where is everything in the universe going? Part of the answer lies in gravity. Galaxies fall toward mass concentrations. But another part lies in something deeper. Space is stretching beneath their feet. It's not just the galaxies moving. It's the stage they stand on, expanding outward. This is the layer of motion beneath all other motions. The motion that sets the overall trend of the cosmos. The motion that shapes the fate of everything. But there's a catch. If the universe were only expanding, logic says it should be slowing down. Because gravity, even weak over huge distances, should gradually reduce the expansion rate. But that's not what we see. It's getting faster. F. The mystery. Expansion is accelerating. In the late 1990s, astronomers studying distant supernovae made a shocking discovery. The expansion of the universe isn't slowing down. It's accelerating. Galaxies aren't just drifting apart. They're drifting apart faster each year. Something is speeding up the stretching of space. Something invisible. Something everywhere. Something woven into the fabric of the cosmos itself. A new ingredient in the universe. A force, or perhaps a property, that pushes space to expand more and more over time. And it leads us to the biggest mystery in modern cosmology: dark energy. A force we don't understand, but one we can measure through its effects on the expansion of the universe. A force that decides the far future of everything. When astronomers first mapped the expansion of the universe, they expected one simple trend. As time passed, expansion should slow down. Gravity pulls things together. Even across billions of light years, that pull should, little by little, reduce the speed at which galaxies drift apart. But in 1998, two independent teams studying the same kind of cosmic lighthouse discovered something that rewrote everything. A. Type EE supernovae, the universe's standard candles. These lighthouses were type Ea supernovae, explosions so bright and so consistent that astronomers can use them as reliable distance markers. They always reach roughly the same peak brightness. So if they look dimmer, they must be farther away. If they look brighter, they must be closer. Two groups, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, measured dozens of these distant supernovae. Both teams expected to find proof that the expansion of the universe was slowing. Instead, they found the opposite. The supernovae were too dim, meaning they were farther away than expected, which meant the universe hadn't slowed its expansion. It had sped up. Saul Perlmutter put it plainly. We expected the universe to slow down. Instead, we found it speeding up. This discovery became one of the greatest surprises in the history of cosmology. Something unknown was accelerating the expansion of space. B. If expansion is speeding up, something must be causing it. Gravity couldn't explain it. Gravity only pulls, it cannot push. Yet the space between galaxies was stretching faster and faster, as though something were encouraging it to grow. Adam Rees said, "Something is pushing the cosmos apart, and we don't yet know what." This was the birth of a new idea. C. Naming the unknown. Dark energy. Scientists needed a name for this mysterious influence. They called it dark energy, not because it's dark, not because it's a form of energy like electricity or heat, but because we don't know what it is. All we know is that it fills all of space. It acts everywhere, and it makes up about 70% of the entire universe. Everything we understand, stars, planets, gas, galaxies, is only a tiny slice of reality. Most of the universe is made of something we've never touched, never seen, never measured directly. A quiet, invisible presence woven into the fabric of space-time. D. Maybe it's the energy of empty space. One idea is that empty space isn't truly empty. In quantum physics, nothing still has fluctuations, tiny blips of energy that appear and vanish. This is sometimes called zero-point energy. It's tempting to think dark energy might be this vacuum energy. But there's a problem. Quantum theory predicts a value for vacuum energy that is 2120 times larger than what we observe. That's a number so large, it defies imagination. The biggest mismatch between theory and reality in the history of science. If dark energy really is vacuum energy, then something is deeply wrong with our understanding of physics. And yet, it remains one of the leading explanations. E. Understanding it. Through images. To make sense of it, imagine space as a vast fabric stretched gently in all directions. Dark energy is the quiet, continuous pull on that fabric. It doesn't come from a source. It doesn't radiate from an object. It simply exists. Everywhere. As long as space exists, dark energy continues to expand it, like a breath that never ends. It doesn't care about galaxies or clusters or superclusters. It works on the fabric itself, F, what it does to the universe. This silent push causes galaxies to drift farther apart over time, clusters to slowly loosen their grip, entire superclusters to slide away from one another. Eventually, galaxies that are visible today will become unobservable. They will recede faster than their light can reach us. Future astronomers, billions of years from now, might look into the sky and see only the fading glow of their own galaxy, wrapped in darkness. That is the long-term consequence of a universe driven by dark energy. G. Bringing it back to you. As you lie here tonight, the expansion of space is not something you feel. It does not lift your pillow or stretch the walls of your room. But on cosmic scales, this silent push shapes everything. It pulls galaxies apart. It stretches the universe wider and wider. It decides the fate of all cosmic structures. While you breathe in and breathe out, the universe grows just a little. A tiny fraction too small to notice, but large enough to accumulate across billions of years. Dark energy isn't pushing galaxies. It is pushing space itself. H. Preparing for the endgame. Big rip, big crunch, big freeze. Dark energy doesn't just change the present. It determines the future. If its strength increases over time, the expansion could accelerate so violently that even galaxies, stars, planets, and eventually atoms could be torn apart. This is one possible fate: the Big Rip. If dark energy remains steady, constant throughout time, the universe will continue expanding forever, slowing slightly, but never stopping. Galaxies will drift into darkness. Stars will burn out. Temperature will fall toward absolute zero. That fate is known as the Big Freeze. And if dark energy changes sign, if it becomes attractive rather than repulsive, then gravity could eventually dominate again. The universe would slow, halt, and reverse. Everything would collapse inward, ending in a fiery contraction known as the Big Crunch. 3 endings, 3 futures, each tied to the nature of a force we barely understand. But that is the power of dark energy. It is the quiet hand on the steering wheel of the cosmos. For the entire story so far, motion has been the quiet engine of the universe. Planets orbit stars. Stars orbit the galactic center. Galaxies flow toward massive basins. Superclusters drift along gravitational rivers. And beneath it all, the fabric of space stretches gently, steadily. But what if that stretching never stops increasing? What if the silent push of dark energy grows stronger with time? This brings us to one of the most dramatic possibilities for the fate of the cosmos, a scenario called the Big Rip. Not an explosion, not a collapse, but a future where the very motion of the universe becomes the thing that pulls everything apart. A. The idea behind the Big Rip. The logic is simple. If dark energy stays constant, the universe expands forever. If dark energy weakens, gravity may eventually overcome it. But if dark energy grows stronger, even slowly, its effects compound exponentially. In that case, expansion doesn't just continue, it accelerates violently. A point eventually arrives when the expansion of space becomes stronger than any force holding matter together. And after that point, every structure in the universe begins to fall apart. One layer at a time. B. The sequence of dissolution. A slow unraveling. If the Big Rip ever comes, it won't happen all at once. It will come in stages, a cosmic timeline of separation. First, galaxy clusters loosen. Clusters like Virgo, Laniākea, and Shapley will no longer stay bound. the gravitational ties between them will weaken. They will drift apart faster than their gravity can hold them. Next, individual galaxies separate. The Milky Way, Andromeda, and the thousands of galaxies around them will no longer form a meaningful structure. The rivers of galaxies will dry up as the flow becomes dominated by expansion. Then, star systems unravel. Within galaxies, the expansion of space will grow stronger than the gravitational pull holding stars in orbit. The Sun would no longer hold Earth, Jupiter, or Saturn in long, sweeping paths. Planets would drift off into the widening darkness. After that, stars themselves lose cohesion. Gravity at the heart of each star would eventually lose its battle. The expanding fabric of space would begin tearing stars apart, not explosively, but like threads pulled from a cloth. Then, molecules are stretched. Chemical bonds, usually unbreakable on cosmic scales, would be strained beyond their limits. Matter itself would lose its shape. Next, atoms separate. Electrons would be pulled away from their nuclei. The simple, stable structures that form reality would no longer hold. Finally, even protons fall apart. If dark energy continues to grow, even the strongest force known, the one that binds quarks inside a proton, would eventually be overcome. 2 decades ago, physicist Robert Caldwell, the originator of the Big Rip idea, said it plainly. If phantom energy exists, it will tear apart galaxies, stars, and even atoms. At that moment, the universe becomes a thin mist of drifting particles, then a thinner mist, then nothing that could be called structure at all. Everything unraveled not by fire, but by motion. See, when would this happen? If the Big Rip is real, and that depends entirely on whether dark energy strengthens, the estimated time is around 20 to 22 billion years from now. That is far beyond the lifetime of the Sun, far beyond the lifespan of Earth, far beyond anything we can emotionally attach ourselves to. It is a future so distant that it becomes oddly soothing. A reminder that whatever happens to the universe, tonight is not the night to worry. D. What the universe would feel like in a Big Rip. If one could observe this process from a safe timeline, it wouldn't look like destruction in the usual sense. No fire, no shock waves, no cosmic collision. Instead, the universe would fade into tension, a constant, accelerating pull. Galaxies would stretch until their shapes dissolved. Stars would lengthen into luminous threads and then wink out. Planets would drift apart like loosened beads. Matter would begin to feel thin, as though the universe itself were sighing outward. It's a kind of quiet, widening, endless, unweaving. A death not by impact, but by stretching. E. A gentle philosophical reflection. If the Big Rip becomes reality, it would be the only cosmic ending driven not by collapse or decay, but by motion itself. Expansion. Once the silent background of the universe becomes the tool of dissolution. In this future, nothing travels to a destination. Nothing orbits. Nothing falls. Everything is pulled away from everything else until nothing is left to pull. The final answer to our guiding question becomes strangely literal. If the Big Rip occurs, everything is going into pieces. Not toward a place, but away from the ability to be a place. Not traveling across the universe, but being stretched out of existence. Bringing it back to you. And yet, this scenario, dramatic as it sounds, is incredibly far away. Far enough that every star now shining will have lived and died before it begins. Far enough that no human, no civilization, no memory we carry will witness it. Tonight, the universe around you is vast, stable, slow, and familiar. You are simply drifting along its timeline, exactly where you should be. Gravity and dark energy might choose a gentler fate. For a moment, let's step back. In the last segment, we explored the most dramatic ending imaginable, a universe torn apart by its own accelerated motion, a finale of stretching. But not every ending tears things apart. Some endings fold everything back together. Some simply let the universe fade, slowly, quietly, into cold darkness. There are two other cosmic destinies that astronomers contemplate. One ends in fire. One ends in frost. And both complete our journey to answer the question we began with. Where is everything going? A. Big crunch. When gravity wins, imagine for a moment that the silent push of dark energy weakens, or vanishes, or even flips sign, becoming attractive instead of repulsive. In that universe, gravity would no longer merely shape galaxies. It would dominate the large-scale fate of everything. If that happens, expansion slows, then halts, then reverses. 1. The conditions. The big crunch requires enough matter and energy to overpower expansion, or dark energy decreasing over time, or dark energy turning into a force that pulls, not pushes. This is a universe where gravity wins the long game. 2. A universe that stops growing. At first, the change is subtle. The expansion rate slows. Distant galaxies stop accelerating away. The Hubble flow weakens. The large-scale structure of the cosmos begins to hesitate. And then, expansion reaches zero. A cosmic turning point. A moment when every galaxy in every direction is no longer drifting away, but beginning to fall back inward. 3. The return journey. Clusters start to approach one another. Galaxies collide far more often. Massive structures drift closer in a complex gravitational waltz. The background temperature of the universe increases as matter compresses. The night sky brightens slowly, not by new stars, but by the accumulated glow of everything packed more tightly together. Space itself begins to fold, curve, and tighten. 4. The final era. Eventually, the universe becomes a vast, collapsing furnace. Stars, dust, planets, black holes, and radiation swirl into an ever-shrinking arena. Temperatures climb to unimaginable levels. Distances shrink until almost every particle in existence occupies the same region of space-time. Some models predict a final state that resembles the beginning. A universe that ends in an echo of the Big Bang. A hot, dense, bright endpoint where everything is compressed into an infinitesimal volume. 5. A gentle reflection. For some cosmologists, the Big Crunch once held emotional appeal. It felt cyclical, a universe that breathes, expand, collapse, begin again. As physicist Roger Penrose has suggested, the end of one universe could, in some models, be the beginning of another. A loop, a rhythm, a cosmic heartbeat. 6. What science says today. Current measurements of dark energy do not favor the Big Crunch. dark energy seems stable, constant, and strong enough to prevent a future collapse. But the possibility still teaches us something profound. Under the right balance, gravity could pull the universe back together. 7. Where is everything going? In a big crunch. In this fate, everything is going back together. Galaxies, clusters, stars, all falling inward. Not into a center, but into a future of increasing density. A universe returning to its own beginning. B. Big freeze. The long fade. But the most likely ending, according to everything we know today, is neither a rip nor a crunch. It is the quietest end imaginable. A future where expansion continues forever, powered by a steady, unchanging dark energy. A universe that grows colder, emptier, and darker with time. A universe that doesn't end in a bang, but in a whisper. 1. The conditions. The big freeze requires. Dark energy remains constant. Expansion accelerates gently but steadily. Gravity binds only small-scale structures. This is the cosmological constant model, the one that fits our best data. 2. The first signs. Distant galaxies drift beyond the cosmic horizon, not because they vanish, but because space expands faster than light can carry their image to us. The observable universe shrinks in content even as it grows in size. Local group galaxies remain bound, but everything else fades from view. 3. The era of stars. For trillions of years, stars continue to be born, burn, and die. But the raw material for star formation gradually runs out. Cold gas gets locked inside dead stars and black holes. New stars become rarer, then cease entirely. 4. The age of remnants. Billions of years pass. All that remains are brown dwarfs, fading white dwarfs, neutron stars, stellar mass black holes, supermassive black holes. The sky becomes darker, not suddenly, but millimeter by millimeter. Light thins, energy disperses. The universe becomes a hushed gallery of cooling cinders. 5. The reign of black holes. Over unimaginable timescales, 1067 years or more, even black holes begin to evaporate via Hawking radiation. One by one, they dissolve into faint, ghostly streams of particles. When the last black hole evaporates, the universe enters its final chapters. 6. The era of almost nothing. If protons decay, the remaining matter eventually becomes a thin sea of electrons, photons, and neutrinos. If protons don't decay, the universe still drifts toward cold uniformity. Temperatures hovering just above absolute zero. Movement slowing, structure thinning. This is the universe moving toward perfect stillness. As physicist Lawrence Krauss once said, the universe will simply fade to darkness. A long, slow whisper. Not a moment of death, but the eventual absence of anything new. 7. Where is everything going? In a big freeze. In this fate, everything is going nowhere in particular, just farther apart, slower, colder, quieter, forever. C. 3 endings, 1 question. Now that we've explored them, let's see the full picture one last time. Big rip, everything into pieces. Big crunch, everything back together. Big freeze, everything drifts into quiet darkness. Our best measurements put the big freeze as the leading candidate. But cosmology is young. The universe is vast. And our understanding of dark energy is still in its infancy. And what does this mean for you? It means every one of these endings lies so far beyond human imagination that they feel more like mythology than danger. They live on timescales where stars age and die, where galaxies merge, where black holes evaporate, long after Earth, the Sun, and even the memory of humanity have passed. Tonight, none of this touches you. The future of all things is cosmically large. Your future, the only one you inhabit, exists in nights like this one, in breaths, in quiet moments, in the soft, silent motion of now. Every story has an ending. Knowing that doesn't make the middle less meaningful. You've covered a lot of ground tonight. You started on your back, on a mattress, in a quiet room, feeling for a moment as if everything around you was still. From there, we walk through an old idea, that we once believed we were the center of everything. We watch that belief shift, gently but decisively, into the realization that we are in orbit, around a star, inside a galaxy, inside a much larger flow. You found the sun's address in the Milky Way, tucked away on a small spiral arm. You looked ahead to a slow-motion meeting with Andromeda, a coming together of two great islands of stars. You followed the local group into Laniākea, along rivers of galaxies flowing toward hidden valleys of gravity and away from vast, empty voids. You stepped out far enough to see the expansion of space itself and the quiet, mysterious pressure of dark energy. And finally, you stood at the edge of three possible endings: a universe torn apart, a universe collapsing inward, or a universe fading into cold, endless night. All of that from the same position you're in right now. The question, where is everything going, turned out not to have a single answer. Each scale, planet, galaxy, supercluster, universe, answered it in a different voice. But what about you? Where are you going? At least for tonight. Right now, you're still in the same place you were when this story began. The sheets haven't moved under you. The pillow is still beneath your head. All the numbers about velocities and distances, thousands of kilometers per second, millions of light years, haven't changed the simple truth that for these few hours, you're allowed to stop. The universe can keep doing what it does best, moving. You, for once, don't have to. All of those cosmic timelines, billions, trillions, even 1067 years into the future, sit far, far beyond the scale of your life. The Big Rip, if it ever happens, is 20 billion years away or more. A big crunch, if gravity ever wins again, would happen long after every star you know has burned out. The Big Freeze stretches so far into the future that human words barely mean anything there. On your timescale, the sun is steady. Earth's orbit is calm. The galaxy is quiet. Nothing out there is going to change your night tonight. No galaxy is about to slam into the Milky Way. No Big Rip is waiting around the corner. The only thing that needs to wind down now is you. Knowing how much the universe is in motion doesn't shrink your life. If anything, it does the opposite. It makes these hours, this small, quiet slice of time, feel more precious and, strangely, more peaceful. Step outside in your mind for a moment. Picture the night sky above your roof, or your city, or the clouds you can't see through. To your eyes, the stars look frozen, as if someone pinned them to a black canvas. Now you know better. You know they're all moving along immense curves, orbiting, drifting, falling through rivers of gravity. You know that even the dark between the stars is stretching. And yet, from here, it all looks still. You're like a tiny point on a ship gliding over a perfectly calm sea. The noise of the day, work, messages, worries, unfinished to-do lists, has been left in the harbor behind you. Out here, the water is flat. The engines hum quietly. And for once, you don't need to steer. Your breathing has probably slowed by now. In and out. In and out. Each breath syncing up in its own small way, with the rotation of the planet underneath you. Your heartbeat is just another soft signal in a universe full of signals. Small, steady, and enough. You don't need to hold anything together. You don't need to keep track of where every galaxy is heading. Gravity and dark energy will do their jobs whether you're awake or not. Tonight, you're allowed to set the big question down. You're allowed to let go of where is everything going and simply rest in the fact that it is going and doesn't need your attention to do it. The cosmos can keep moving without you watching. If you zoom back in one last time, the answers stack up quietly. On the Earth scale, you're going around the sun. On the galactic scale, you're circling a black hole at the heart of the Milky Way. On the supercluster scale, you're sliding with countless other galaxies toward a hidden valley of gravity. On the cosmic scale, you're being carried outward by the expansion of space. We don't yet know which ending the universe will choose. Rip, crunch, or freeze. We don't know exactly how the last chapter will read, but we know enough to say this. Wherever everything is going, you don't have to go there tonight. For tonight, the only place you need to go is to sleep. So if you haven't already, let your eyes close. Feel your body sink a little deeper into the mattress. Let your thoughts thin out, like galaxies drifting into the dark. In and out. Each breath, a small orbit of its own. You are safe. The universe is quiet enough for you to sleep. Let it go where it will. For now, just rest. Where is everything in the universe going? Maybe you don't need the full answer tonight. The only place you have to go now is to sleep.